So here we have an incompressible fluid, and we're given the density, which is equal to 0.00209 slugs per feet cubed, and it flows from a tank at 0.5 psi through a 20-foot long pipe. It has a diameter of 1 inch, and then through a pipe that's 0.5 inches in diameter, and this pipe is also 20 feet long. And we're given a friction factor for both the pipes equal to 0.015, and what we're asked for is the flow rate. And here we're going to assume that the pipe exits into the atmosphere, and we're going to neglect minor losses. So let's start by labeling the different parts of the diagram. So we're going to call the tank here 0. We're going to call the first pipe here 1. Our second pipe is 2, and the exit is 3. So let's do an energy balance between 0 and 3. And here we have that our P is going to be equal to our pressure. Our gamma is going to be equal to our specific weight, which is density times gravity. Our V is velocity, our G is gravity, and our H sub L is the head loss. And if you remember from the problem statement, this is only major head loss because we're neglecting the minor. So now let's simplify this. So since it exits into the atmosphere, P3 is going to be equal to 0. Because we have a tank, a large tank going into a small diameter, V0 is small enough that we can basically call it 0. In addition, it's horizontal, so our Z0 is equal to Z3. So we know that V2 is equal to V3, and we also know that the total head loss is equal to the sum of the head loss in the two pipes. So that head loss is equal to as follows. So this is equal to our total head loss, the head loss in pipe 1 and the head loss in pipe 2. So because of continuity, we can write V1 in terms of V2. So our V1 A1 is equal to V2 A2, and therefore V1 is equal to V2 A2 divided by A1. And we can simplify this even further, that this is equal to V2 D2 squared divided by D1 squared. So V1 is equal to 0.25 V2. And does that make sense? Yes, V1 should be less than V2 because the diameter is greater. So let's put this all in one equation where we write our specific weight in terms of density. So our L1 is equal to L2, which will just be L in this equation. Our friction factor is the same, and that's our 0.015. And so when we put our numbers in, we can solve for V2 right here. So first of all, don't forget to put the diameters and pressure in terms of feet, and I'll show you the here 0.5 psi has to be multiplied by 144 because that's square inches per feet squared, and that's going to be equal to 0.0088 V2 squared. And so now when we solve for V2, that's going to equal 90.4 feet per second. But remember that we're looking for Q, so Q is equal here to V2A2, where our area is equal to pi d2 squared divided by 4. And we put our numbers in, and our Q is equal to 0.123 feet cubed per second. Note I did this with velocity 2, but if you go back and you look at this in series, what you'll find is that our Q's stay the same, so that Q1 is equal to Q2, so we could have solved it that way as well.